Today, I'm honored to present my master's project report titled Train-Centric Graph Neural Networks for Multi-Step Railway Delay Prediction Model. This study focuses on multi-step railway delay prediction in high-speed rail operations. Specifically, this study formulates future stop delay prediction as a train-centric graph learning task. Today's presentation is organized into 4 parts. First, I will explain the background, the research details, experimental results, and analysis. And then I will discuss the implications, limitations, and the future work. The motivation of this study comes from a practical problem in high-speed rail traffic management. In railway operations, delay affects dispatching decisions and passenger information. However, a delay is not only a local event. Once one train is delayed, the delay may cascade to following trains, affect track capacity, and create additional schedule constraints. Rail operators like KORAIL need to know how will this delay evolve and propagate over future stops. Therefore, the goal of this study is to predict how the delay of an active train will evolve across its downstream commercial stops. Related literatures can be summarized into 3 streams. First, railway delay prediction studies have shown that delay prediction is important for real-time traffic management, and that delays propagate through operational dependencies and infrastructure constraints. Second, sequential forecasting studies show that LSTM and Transformer models have different temporal modeling strengths. Third, graph-based transportation studies shows that GNN can represent relational and spatial temporal dependencies. However, some limitations remain. Many studies focus on station level, next station, or fixed lead time prediction rather than active train level future stop sequences. Also, graph structures, temporal module, and prediction target are often changed together, making it difficult to isolate component effects. Finally, most studies rely mainly on average performance and do not sufficiently analyze delay regime-dependent model behavior. From this, we found the research gap, controlled comparison of temporal decoders under a fixed train-centric encoders. Based on this research gap, the main research question is, when a train-centric spatial encoder is fixed, does predictive preference between temporal decoder architectures vary across delay regimes? So this study makes 3 contributions. First, it reformulates multi-horizon future stop delay prediction as a train-centric graph learning problem. Active trains are represented as nodes. Train-to-train operational dependencies are represented as GH, and the prediction target is the delay sequence over downstream stops. Second, it establishes a controlled comparison. The spatial encoder is fixed, while the temporal decoder is varied between LSTM and Transformer. This allows us to isolate the effect of temporal inductive bias. Third, it shows regime sensitivity. The results show that architectural preference is not uniform across delay regimes. This slide defines the prediction task. At snapshot time t, we observe an active train I, and the objective is to predict its arrival delay over the next 6 downstream commercial stops. This output is not a single next station delay, but a multi-horizon delay sequence from H1 to H6. Because not every train has 6 remaining stops, we use a binary horizon validity mask. Only valid future stop positions are included in the loss and metric computation. So the task is to predict the downstream delay sequence of each active train from the train states at time t. This study used real KTX and SRT operational data from 2025. The dataset contains about 4 million operational records and 150,000 unique train 1 instances. Since the low logs are event-level records, I converted them into regular 2-minute snapshots. This produced 223,000 snapshots. From these snapshots, I constructed a train-centric graph forecasting corpus. This is a sample of the law operation law from KORAIL. It contains train ID, type, direction, station name, scheduled and actual time, delay, distance, and so on. We used all of this except the delay reason code because it can cause data leakage as it is inserted later by dispatcher. One of the key components of this study is the train-centric graph. At each snapshot, the nodes are the active trains currently operating. The edges represent three types of train-to-train operational dependencies. First, precedence represents same direction following relationship with a track section. Second, downstream blockage represents route overlaps anticipated with the next three sections. Third, coupled internal represents the operational dependencies between trains involved in coupling or splitting at Dongdaegu or Iksan Station. Initially, explicit conflict point competition was also considered, but it was ultimately excluded because the Korean high-speed railway operates on double-track sections where direct head-to-head conflicts are rare. To construct the graphs, we use the PyTorch geometric library. Each graph sample consists of several components. The node feature matrix X represents the current operating state of each active train. The edge index defines directed train-to-train dependencies, and the edge attribute matrix contains relation type indicator and numerical proximity variables. For each horizon, the numerical quark tensor includes planned arrival remaining time, planned departure remaining time, remaining distances, and pair station flag. In addition, the future station index is passed through a station embedding. The target delay Y is the actual arrival delay at each time, and the horizon mask indicates valid prediction positions. So the model combines current interaction encoding with future stop specific current information. This is the overall model architecture from input to output. Raw operation data are transformed into train-centric snapshot graphs. Each graph is passed through a GATV2 spatial encoder, which produces a context vector for the target train. The same context vector is then passed to either an LSTM decoder or a transformer decoder. The output is delay sequence for the 6 future stops. The methodological focus is the controlled encoder-decoder comparison. The GATV2 encoder captures operational dependencies among active trains and produces a common context vector. Then, two different temporal decoders are compared. The LSTM decoder performs recurrent sequential decoding and accumulates information step by step across downstream stops. The transformer decoder performs parallel attention-based decoding and models interactions across horizons in parallel. Because the spatial encoder is fixed, the comparison mainly isolates the effect of temporal decoder inductive bias. The baselines are designed for component-level interpretation. Persistence copies the current anchor delay as a deterministic baseline. Node query MLP removes graph interaction and uses only target local features and the future stop query. GAT-MLP uses the GAT-V2 graph encoder but removes the sequence-aware decoder like LSTM or transformer. Station sequence LSTM is a station-centric sequence baseline. These baselines create 3 constructs and allow us to test the value of graph interaction, sequence-aware decoding, and train-centric representation. The dataset is split chronologically into training, validation, and test periods. The training set covers 17% and the validation and test sets cover 15% each. Random splitting is avoided because adjacent 2-minute snapshots are strongly correlated and could cause temporal leakage. The learned models are evaluated over 3 independent training runs with differences. So, the delay error is reported as mean plus or minus the standard deviation. For evaluation, MAE is used as the main metric and RMSE is used as a complementary metric. The evaluation is conducted in 3 layers: overall, horizon-wise, and delay regime analysis. First, let's look at the overall test performance results. GAT LSTM achieves the lowest MAE and RMSE with an MAE of 100 seconds and an RMSE of 155 seconds. This suggests that train-centric graph interaction encoding combined with sequential downstream decoding is effective on average. The second observation is the node covering MLP and GAT MLP shows almost identical performance. This means that graph encoding alone is not the main source of the gain. Third, station sequence LSTM remains close to persistence, suggesting that sequence modeling alone is insufficient when the representation is not train-centric. Overall, the main gain comes from combining train-centric interaction encoding with sequence-aware downstream decoding. Next, let's look at the horizon-wise performance. For every learned model, prediction error increases as the horizon becomes longer. This is effective because uncertainty accumulates across downstream stops. GAT LSTM shows the most stable horizon-wise profile and its relative advantage become more visible at longer horizons. This suggests that LSTM-based sequential downstream decoding is well aligned with ordered delay propagation. The table on the right shows that later horizons contain fewer valid samples. Therefore, horizon-wise results should be interpreted together with the valid sample distribution. Finally, let's move on to the delay regime analysis. Although GAT LSTM is the strongest model overall, but the result shows that model preference is not uniform across delay regimes. Under non-positive and very wide delays, persistence remains highly competitive because the current delay state is already a strong reference. Under normal delay conditions, GAT LSTM achieves the best MAE. This suggests that recurrent downstream decoding is effective when delay propagation is relatively structured and gradual. However, as disruption severity increases, GAT LSTM's advantage weakens. In extreme delay cases, even station sequence LSTM performs best, suggesting that station-level signals may become informative under rare extreme disruptions. This suggests that severe disruption may involve broader operational dynamics that are not fully captured by local train-to-train sequential propagation alone. The key message is that there is no single universal best architectures. Performance is tied to the operational delay regimes. Therefore, railway delay forecasting should be understood as a regime-sensitive forecasting problem, rather than as a simple average ranking problem. And one more thing, this slide shows that attention topology for the KTX 36 train using the GAT LSTM model on a specific day. The attention topology shows which trains the model focuses on when predicting the delay. The results suggest that the graph encoder does not simply average all neighbor trains. Instead, it selectively attends to adjacent interacting trains. Of course, these attention patterns should not be interpreted as causal evidence. However, this analysis provides operational interpretability through attention analysis and supports the plausibility of the train-centric graph framework. To conclude, I would like to summarize the main discussion points. First, train-centric representation matters because future stop delay is predicted for an active train, not for a station level or aggregate network state. Second, LSTM works well on the structured delay propagation because it carries delay information across successive downstream stops. Third, a severe disruption can partially break the regular sequential structure. So, GAT LSTM's advantage weakens and alternatives become more competitive. First, graph encoding alone was not enough, as shown by the similar performance of load query MLP and GAT MLP. Finally, station aggregation alone was insufficient because it does not preserve the relational identity of each train. Therefore, the main finding is that predictive gain comes from combining train-centric interaction encoding with sequence-aware downstream decoding. So, the main practical implication of this study is need for regime-aware model selection. GAT LSTM provides strong and stable performance across the overall distribution and under normal conditions. However, under larger disruption, alternative architectures become more competitive. So a practical system may require a separate regime identification module and an adaptive ensemble design. Of course, there are also some limitations. First, this study is based on just 1 year's data from the relatively controlled Korean high-speed railway. Second, exogenous factors such as weather, signal failure, or passenger issues were not included. Third, this study does not implement a real-time switching or adaptive ensemble system. For future work, therefore, the framework should be validated in broader railway settings, enriched with additional operational context, and extended toward adaptive regime-aware forecasting methods. These are references used in this study. Thank you for listening.